for the conference dinner of the Chemometrics conference. I gave my talk today, and what I'd like to do now is I'd like to give my talk again. So here it comes. My aim in this presentation is to convince you that compositional data analysis, or CODA as it is often called, is really quite simple and is basically applying all that you already know about statistics to data that have just been transformed. Compositional data are non-negative, multivariate data where the absolute values of the data carry only relative meaning. Since the absolute values are not relevant, compositional data are often expressed with a constant sum constraint. That is, the values for each multivariate sample are either observed as summing to a constant, usually 1 or 100%, or are re-expressed as values relative to a total that is irrelevant to the research objective. For example, the composition of a chemical sample where the amount sampled is of no interest. Here are the three giants on whose shoulders we stand. From the right, Jean-Paul Benzécry from France, one of my thesis advisors. Then the Scottish statistician John Aitchison, whom I met in 2000, and we wrote an article together in Applied Statistics on compositional biplots. And Paul Levy, molecular biologist at Janssen Pharmaceutica in Belgium, one of the co-founders of the discipline of Chemometrics, whose ideas on CODA actually predated Aitchison's. He was the only one, as far as I know, who made contact with one of the others, in that he went to visit Benzécry's group in Paris to learn about correspondence analysis, and this led to his idea to weight the parts in CODA as was done regularly in correspondence analysis. Paul and I met in Barcelona, and I also visited him in Belgium, and we wrote a paper together in the Journal of Classification. As I will show later, there is a very close relationship between Levy's and Benzécry's work. So what is the big issue in CODA? It's mainly what Aitchison called subcompositional coherence. If components of the composition, called the parts, are added or removed and the compositions closed or normalized again, that is, re-expressed to sum to 1, then the data change. So the usual statistics such as means, standard deviations, and correlations are changed. This is usually illustrated with very small examples, which exaggerate the problem. And I've fallen into this trap too, since the problem becomes diluted in datasets with very many parts. So here we have a fatty acid dataset with 4 parts, and if we remove the last part, all the values change. And this affects the means, the standard deviations, and the correlations, which change value and can even change sign. Here we see the different correlation between the same 2 fatty acids in the 2 datasets. A way to make CODA coherent, proposed by both Levy and Aitchison, is to consider ratios between the parts, since these do not change. Here we see the values for the 6 ratios of pairs of parts, and below the values of the 3 when the last part is again removed and reclosed to sum to 1. The values are identical. Then we take logarithms of the ratios to get so-called log ratios. Log transforming is important for many reasons: to make the data interval scale, to equate a ratio and its inverse apart from a sign change, and reduce skewness. The only drawback is that zeros are now not allowed, and that is a real headache, since compositional data often have many zeros. This brings us to the main theme underlying this presentation. CODA is simple. There are a whole lot of methods that we know for both unsupervised and supervised learning, many of which are listed here, but there are many, many more. The only novelty in the log ratio approach to CODA is the choice of log ratio transformation, and then to know how this choice affects the interpretation of the results. There are a few choices for the log ratio transformation, and the 3 simplest and most useful are listed next. So now for computing log ratios, we have to consider compositions with strictly positive values. In general, a composition will have J parts, and a dataset will consist of I compositions. So the original dataset is an I by J matrix. The simplest log ratio transformation is the pairwise log ratio, or PLR, the log ratio of two parts. Now there are half times j minus 1 of these PLRs. So if we compute them all, this would blow up the number of columns of data. But the rank of this very wide matrix is only j minus 1. That is, if you have just j minus 1 linearly independent log ratios, you can compute all the others. The second useful log ratio is the additive log ratio, or ALR, where the denominator is fixed, called the reference part. There are thus j minus 1 additive log ratios in any particular set, and they are linearly independent, but there are j possible choices for the reference part. Finally, centered log ratios. These make the reference part the geometric mean of all the parts. There's only one set of j CLRs, but they are of rank j minus 1 and so not linearly independent. But this represents no complication in using them in regular statistical analysis. In fact, they are the variables of choice for doing principal component analysis and making biplots. And if covariance matrices of CLRs are required for inverting, then generalized inverses are used instead of regular ones. Three applications are now given to show how simple CODA is for doing both unsupervised and supervised analyses, using different choices of these log ratio transformations. The first is a geochemical dataset, 270 samples and 22 elemental parts. The second is a very wide genomic dataset, only 89 samples, but 3,937 microbial genes as parts. The third is a microbiome dataset, 975 samples and 48 microbial genera, where the object is to predict Crohn's disease. In this third example, the relationship to correspondence analysis will also be demonstrated. Okay, the first dataset, the geochemical dataset, this has been fully analyzed in this open access article by two geochemists, Eric Grunsky, Bruce Charsgaard, and myself, using a workflow which we call GeoCoda for geochemical compositional data analysis. Now, this is an attempt to show the raw compositional data for the 270 samples, which come from 5 successive phases of volcanic eruptions. The third phase, early Jolifeu labeled EJF, has yielded more macro diamonds than the other phases, so it will be useful to try to predict that phase from the compositions. Here we see that it is only possible to see the data for the 9 major elements. The others are too small on this linear scale of proportions. But by making a transformation involving logarithms, all the elements can be seen, but the scale is now nonlinear. Nevertheless, this helps in comparing the phases, and there are clear differences when changing to the EJF phase. In geochemical datasets, there are certain known groups of elements that can be amalgamated by summing. In this case, there are 3 that involve 19 of the 22 parts. Their values can be shown in star plots where each part has been rescaled between the lowest and highest median values for the 5 phase groups, and there are clear differences between the groups. When there are 3 parts, in this case the 3 amalgamations, they can be represented in ternary plots. The mantle amalgamation has such high percentages that all the points are forced into the mantle corner of the triangle, so only that top tip of the triangle is shown here. On the right is the centered ternary plot, where it is easier to see the phase differences. However, even easier and more interpretable is a simple scatter plot of 2 log ratios. In fact, 2 additive log ratios with mantle as the reference. Here the convex hulls are shown around the 5 groups of points, as well as a 99% confidence ellipse obtained by bootstrapping. Mantle is a convenient reference as it has very low variance in its log, which means that the variability is almost entirely in the numerator parts and a scatter plot of log kimberlite versus log crustal shows practically the same configuration. Unsupervised learning on multivariate data typically uses clustering or dimension reduction. Here are the results of k-means clustering on the 270 samples according to their log ratio distances. These are Euclidean distances between the samples based on all their very many pairwise log ratios, but it is mathematically equivalent to use centered log ratios, which is much more efficient. The k-means for numbers of clusters from 2 to 10 shows an increase as expected in the between cluster sum of squared differences. But for diagnostic purposes, to choose the number of clusters, it is easier to look at the increments shown on the right, and then select the number of clusters using the elbow rule, as is often done in PCA. Here I illustrated with a real elbow, borrowed from a life-size artificial skeleton in the anatomy department of the health sciences faculty in Tromsø, North Norway, where I was giving a course. It is clear that 5 clusters are suggested. So cross-tabulating the 5 clusters with the 5 phase groups and assigning the clusters to the most frequent group results in 67.8% correct assignments. Since some authors propose doing the k-means in a reduced dimensional space, we find that the percentage increases to 71.1% correct assignments in a 2-dimensional space found in a PCA of the CLRs. And this PCA of the CLRs I will show in just a minute. For clustering the parts, this is usually done by applying regular agglomerative algorithms to the matrix of CLRs. But this is a counterintuitive way of combining parts in most applications. What is more intuitive is to combine by simply summing the parts, that is, amalgamating them. Although some authors say you shouldn't amalgamate by summing, but by geometric means, this article refutes this by showing that it presents no problem to amalgamate parts in a compositional framework. When 2 parts merge by summing, some of the log ratio variance is lost. So the algorithm combines 2 parts that reduce the log ratio variance the least. The vertical scale then goes from 0 variance lost to all variance lost. In this case, the total variance at the top is equal to 0.1132. To conclude this section on unsupervised learning, this is the reduced dimensional space of the CLRs mentioned earlier. This PCA of the CLRs is called log ratio analysis, or LRA, since it is equivalently the PCA of all pairwise log ratios. This PCA biplot is not interpreted in the usual way, in terms of the parts, but rather in terms of the pairs of parts that are linked, which represent pairwise log ratios. For example, an imaginary arrow from LA at the top to NI at the bottom represents the pairwise log ratio log of NI over LA. And this log ratio would be higher on average in the phase group EJF, which is in the direction of that ratio. And now for supervised learning, where a response variable is available. Methods from this paper will be used by Jean-Marc Coendes and myself, as well as multinomial logistic regression and various tree methods. The response variable will be the 5 phase groups that we want to predict from the mineral compositions. First, the prediction of EJF. Since it is the important diamond-bearing phase, hence using logistic regression. In this paper, simple pairwise log ratios are selected stepwise, either from the pool of all PLRs, of which there are 231 in this application, or from the pool of non-overlapping PLRs, which means that no more than 11 PLRs can be chosen, or from the pool of ALRs, where the first step determines the reference part. The following results use the strictest Bonferroni stopping rule for the stepwise process, which is stricter than both AIC and BIC. Here you can see the log ratios that were selected. using MJ over LA and MG over LA and MG over V for methods 1 and 3, and then the non-overlapping MG over LA and NI over V for method 2. The scatter plots show clearly that EJF is being well separated from the other groups. The logistic regression models are shown here. And to make the interpretation of the second model, for example, more transparent for the geochemist, a contour plot of the probabilities of predicting EJF is shown, back transformed from the predicted log odds, and using the two ratios, not the log ratios, as axes. One can see the 0.5 probability contour line above which EJF is predicted, and then the 17 misclassified samples on either side of that contour, which amounts to 6.3% error. At the bottom, it is pointed out that any model using log ratios reduces to a log contrast, which is a linear combination of the log transformed parts with coefficients summing to 0. An alternative way of predicting is to use a classification tree that selects ratios. Here the log transform is not necessary. The misclassified samples are only 7 now, 2.6% error. Also shown each time is the cross-validation error rate. For predicting all 5 phase groups, either modeling using multinomial logistic regression is used or a classification tree. The methods perform similarly, with multinomial regression doing slightly better on the cross-validation. Finally, random forests almost always give a better performance, but produce no single model, just predictions. Here the cross-validation is done on so-called out-of-bag samples from the bootstrapping that produces the random datasets, giving 7.2% misclassification, and a rate of 11.2% on a holdout test set. Notice this is the only time in all the analysis presented here that performance on a test set is measured. Now we move on to the very wide matrix of the microbial genes in the small sample of rabbits, and the results are those contained in this article in Frontiers in Microbiology. In this wide matrix of 3,971 parts, there are almost 8 million pairwise log ratios. This is where ALRs can be profitably used. The quest is to find the best reference part. The criterion will be the closeness of the ALR geometry to the log ratio geometry, which is conveniently measured by the Procrustes correlation. The theory behind this correlation is not easy to find in the literature, so it is summarized here. To measure the closeness of two multivariate geometries according to their principal coordinates, you first center, then rescale and rotate the geometries to minimize the least squared differences between the two sets of coordinates. The correlation is then just the regular correlation between these fitted coordinates. So every set of possible ALRs is computed, and there are 3,971 of them, and two important statistics are plotted against each other: the Procrustes correlation versus the variance of the logarithm of the reference part. In this case, we have a double success, since the highest Procrustes correlation and the minimum variance of the log reference part are achieved for the same microbial gene, MG856. The very high Procrustes of 0.9991 means that using MG856 as a reference will give practically identical result as if we used all the pairwise log ratios. And then the low variance of the log of MG856 means that the ALRs are almost the same apart from a small shift as the logs of their numerators, which makes the interpretation much easier. Here we see the three analyses which look identical: the PCA of the CLRs, that is the log ratio analysis or LRA, the the PCA of the ALRs, and the PCA of the log numerators. Just the samples are shown with a group identifier and confidence ellipses, showing that one laboratory significantly different, which was subsequently corrected for in the analysis. There were different laboratories doing the gene sequencing, and one is seen here to be significantly different. The final example concerns a microbiome dataset, 48 genera of bacteria observed on the 975 human samples, with a categorical response having Crohn's disease or not. This dataset exists in two versions published by the same authors, with the same dataset named Crohn in two R packages. One is the original dataset with 28.8% of the data equal to 0, and another one which I will call modified Crohn, where 1 has been added to every value in the dataset so that there are no zeros and log ratios can be computed. The LRA of the modified Crohn dataset shows a clear distinction between the Crohn group and the non-Crohn group, practically on the first dimension. So any log ratios that link pairs left to right would likely be distinguishing the groups. Now, for supervised analysis, predicting Crohn using logistic regression, the three ways of Koenders and Greenacre are implemented for stepwise choice of log ratios. First, choose from any of the 1,128 possible pairwise log ratios. The results are shown in a directed graph with edges pointing from the denominator to the numerator of the ratio. 8 log ratios are chosen, involving 15 parts. Here we see that Streptococcus was chosen in 2 log ratios, which are thus overlapping. Second, choose only non-overlapping log ratios. Again, 8 log ratios are chosen, but these involve 16 parts because they are not overlapping. The stopping rule is always according to the strict Bonferroni criterion. Third, choose a subset of additive log ratios. Roseburia is chosen in the first step as the reference part, so all parts are connected to it in the graph. Here, 9 log ratios are chosen, but these involve only 10 parts. Showing the estimated coefficients for this third solution with 10 parts, that is the ALR solution, the logistic regression coefficients on the log ratios are converted to those of a log contrast, and these are shown on the left. The plot on the right shows the coefficients converted to multiplicative effects on the odds of Crohn's disease, along with confidence intervals. As expected, no confidence interval crosses the boundary of 1, which represents no effect. To conclude this talk, the surprising connection between compositional data analysis and Benzacre's correspondence analysis. Now, correspondence analysis is essentially the analysis of a compositional data matrix with weights on the rows and the columns. After meeting John Aitchison in the year 2000 and Paul Lewy just a few years later, I realized that correspondence analysis and log ratio analysis were not separate methods, but connected by the Box-Cox transformation. In fact, without giving specific details, it turned out that with the Box-Cox transformation of the data, CA converged to LRA as the power parameter tended to 0. I already mentioned these three fathers of compositional data analysis, Benzacre, Aitchison, and Lewy, who can now be said to be linked by the venerable Anglo-American pair Box and Cox. This could be stated pictorially as the limit as lambda tends to 0 of Box-Cox of Benzacre is Aitchison and Lewy. There is a linguistic equivalent to this fantastic theorem. The function George David tends to anglicize first names. The limit as lambda tends to 0 of George David of Jean-Paul is equal to John and Paul. This suggests an alternative transformation for compositional data that admits zeros, what I call the chi-power transformation. Chi for the chi-square standardization from correspondence analysis, and power for the Box-Cox power transformation. Details are in a paper to appear soon, where convergence to the CLR is proved. Now, the name chi-power itself has been used for some commercial products. So search for Michael Greenacre in Google and you'll find the preprint. Data zeros are what I've called the Achilles heel of CODA. Many data sets have lots of zeros. For example, the present original Crohn data had 28% zeros. Researchers generally brush this away with a simple statement that zeros have been replaced using one of the many existing imputation algorithms available for compositional data. Others use different approaches, for example, modeling compositions using the Dirichlet distribution. The chi-power transformation does not need zero replacement, but with smaller powers, the transformation starts to break down, seeing that the log transform is the limit. The idea is to find the power lambda where the chi-power transform is the closest to the log ratio transform. The effectiveness of the chi-power transform as an approximation to the CLR is then again measured by the Procrustes correlation on the geometry of both the samples as well as the parts, measuring closeness to isometry and coherence. For the unsupervised dimension reduction, the power lambda that makes the chi-power transform closest to the CLR, that is with the highest Procrustes correlation, is the fourth root transform lambda equals 0.25. On the left is the log ratio analysis on the modified Crohn data. On the right, the PCA of the chi-power transform data with no zero replacement. The Procrustes correlation is 0.905. The advantage on the right is that no zeros were replaced and the interpretation is directly on the parts, not on ratios. For the supervised prediction of Crohn, the chi of chi-power is no longer necessary, since it's just a scale change and the power lambda rather serves as a tuning parameter for improving the prediction. Here is a comparison between the results given by Kai et al. From their CODA for Microbiome package, using all the pairwise log ratios as predictors and imposing the elastic net penalty to select a small set. They report area under curve, AUC, so we do the same using our stepwise log ratio selection, method 1, as well as the chi-power, which turns out to have optimal prediction when lambda is equal to 0.28, almost the same as before. Kai et al. Choose 27 log ratios with elastic net, involving a total of 24 out of the 48 parts. Our stepwise selection chooses only 11 log ratios, involving 19 parts. Stepwise selection of the original parts with power lambda 0.28 chooses the least number of parts, only 14. Yet its performance statistics are similar to the others, and it is the most parsimonious. Well, that is the end of my talk. I here give a lot of references relative to this presentation, but the main ones are the most recent ones. So finally, here are some takeaways from this talk. Compositional data analysis is simple. All you need for Aitchison-style compositional data analysis to ensure subcompositional coherence are pairwise log ratios, PLRs, centered log ratios, CLRs, and additive log ratios, ALRs. Zeros are a big problem for CODA. Alternative approaches try to cope with the zeros, adapting the method to the observed data, rather than changing the observed data to adapt to the method. The Kai power transformation is one such alternative approach, combining the Box-Cox power transformation with the chi-square standardization, and needs no zero replacement. Subcompositional incoherence in alternative approaches becomes diluted as the number of parts increases. This is important for data in the omics area, where coherence is much less of an issue. And finally, a piece of advice to make your lives easier. I reiterate that if you want to follow Acheson's style of compositional data analysis, all you need are pairwise log ratios, centered log ratios, and additive log ratios. They solve all your needs. Nevertheless, there is an industry to create more complicated log ratios using ratios of geometric means. But I can assure you that they only introduce complexity into the interpretation without giving any additional analytical benefit. Remember that simple is better than complicated. Less is more, and especially remember Occam's razor. Thank you very much. Merci beaucoup.
Well, I hope you liked the talk. Now we're going to continue with our lovely cruise on the Loire River in France, near Nantes. Okay, thank you.